Hey guys, in this video we're going to be talking about Chapter 4, Section 2, comparing exponential and linear functions. Alright, so let's remind ourselves what linear functions look like. So linear functions have the form y equals mx plus b, where m is the slope or the rate of change, and b is our y-intercept, or the initial value. You can think of it like that as well. So if a function has this form, when you simplify as much as you can, it's linear. On the other hand, so we talked about exponential functions last time. So exponential functions, we talked about growth and decay, and both of those functions had the form y equals a times b to the x, where a was our initial value. Another way you can think of it as the y-intercept as well. And b was our base, and this was the growth or decay rate, depending on if it was bigger than 1 or between 0 and 1. Okay, so that's what these two things look like. So if we're going through these equations or these functions and we want to know which one is linear, which one's exponential, well, which of these three can be rearranged to look like that? Y equals mx plus b. Well, it's going to be this one, right? Because if we rearrange this so the negative 3x is in front plus 2, then we can see here that negative 3 is m because it's attached to the x, and 2 is b because it's just the constant number added after. So this is linear. Okay, so that one's linear. What about the first one? So the first one is in the form of y equals a times b to the x, right? And in this case, our a is 2 and our b is 3. So this one is exponential. And finally, we have 1/2 t squared. Now this is going to be neither, because in order for us to have an exponential function, we need a variable in the exponent, which we don't have. And this is not linear because of the 2 in the exponent. Linear functions have to have an understood 1 on the exponent of the variable. So this is going to be neither linear nor exponential. Alright, so as I mentioned, linear functions have the form y equals mx plus b, where m is our slope / rate of change, and b is our y-intercept or our starting value. Okay, so we're going to talk about how linear functions and exponential functions are similar and different. And one thing that is similar is that they do both show growth or decay, right? So linear functions do illustrate growth or decay. They're just straight lines. And if the line is sloped up like this, so if m is positive, we slope up like this, and this shows growth. On the other hand, if m is sloped this way, so as time goes on, if we're decreasing, this means that m is negative, and this shows a decrease or decay, if you like to think about it like that. So linear functions have growth and decay, just like exponential functions. However, the key difference is that linear functions are super nice because their rate of change doesn't change, right? It's constant. The slope is always constant. That's how we get that straight line, because if we pick 2 points on the line and we take the slope between those 2 points, it's always going to be the same. It's always going to be m, no matter where those points are. So like even if they're super, super close to each other, like that, we take the slope, we get the same answer for every 2 points that we choose. Okay, so the growth is constant. It stays the same all throughout time. And we can model situations with linear equations. Consider the following. If we start with $20 and save $5 per day, that's a linear situation. Why? Why is this a linear situation? Because our amount is changing, the amount of money that we have. Actually, let's write that. The amount of money that we have is changing by a set amount each day. So this is linear because we're increasing by $5 each day. That's a fixed amount that we're getting each day. So, if we were to make a T-chart for this, if we were to make a little XY chart, well, if we're thinking about our X as our days, maybe we can call it D, and then Y could be the money. We made a little T-chart for this. On day 0, we had $20. On day 1, we saved 5, so we had $25. On day 2, we have $30. Day 3, $35. And we can see that we're increasing by a set amount. We're increasing by $5 each day that passes. So that's what makes linear functions special, is that the amount that we're increasing or decreasing by per unit of time is always the same. And we can graph linear functions. We've already seen this before with piecewise functions, and then prior to that in intermediate algebra we talked a lot about graphing lines with slopes and y-intercepts and stuff, but the graph of a linear function looks like a line, and that's the idea. So exponential functions versus linear functions. What's the same, what's different? Well, what's the same is they both have rates of change. In a linear function, the rate of change is constant. Both of them also have an initial value, a starting value. So this is our initial value here. And so wherever we start, depending on what the slope is, that's how much we're increasing or decreasing by per unit of time. Alright, so that's a linear function. So let's next consider exponential functions. So we talked about these last time. So we were given two things, right? For an exponential function, we have a, which is the initial value, and the y-intercept, just like it is in a linear function. So both of those have that in common. They both have a y-intercept in their form. And b was the growth or decay rate, which was 1 plus or minus the percent change. So b is called b in the exponential function because b is also called the base. So b is the base of the exponential function. And the growth or decay does depend on b, but it's not a constant number like it is with the linear function. M was the rate of change. B is the growth or decay rate, but the amount that it's changing, the amount that your substance is changing per unit of time is constantly changing. So for instance, let's look at the following scenario. You start with $20 and you grow your money by 5% each day. So this is different from the linear situation because we were growing our money by $5 each day. But now we're growing by 1%. So day 1, or maybe day 0 actually, how much money are we going to have? Well, on day 0 we're going to have $20. On day 1 we've grown our money by 5%. So we're going to have $20 plus 5% of 20. And that's going to give us $21, right? So let's see. I believe that is... Yeah, okay. Yeah. Alright, just wanted to double check myself. Sometimes I do that. On day 2, we're going to have 21 plus 5% of 21. So it's going to give us $22.05. And we can keep going like this to see how our money grows after day 3, day 4, and so forth. So notice that unlike the linear case, we're not growing by a set amount, right? In the linear case, we are growing by $5 per unit of time, per day. We are growing by $5. But here we're not. We're not growing by a set amount. However, if we look at the ratios, okay, if we look at the ratios between these numbers, it's going to be the same. So if we look at the ratio of 2205 to 21, that's going to give us 105, right? In a similar way, if we look at the ratio from 21 to 20, that's also going to give us 1.05. So the multiplier is the same. It's 1.05, and it's going to stay the same throughout here. And notice that this number right here, this constant multiplier, is our base. That is our b. So b is going to be the constant multiplier. Right? So in the linear case, we're adding a set amount, all right, for every unit of time. We're adding a set amount to the output. But in the exponential case, we're multiplying by a set amount, okay? That's where this constant percentage is coming from. Okay, so that is an exponential function, and we can see it here. We're not going to really talk about the actual function itself and the shape of the graph, in terms of the shape of the graph, but, we're going to cover that next time. But just, know that this is kind of the basic shape of what exponential growth looks like, as opposed to a linear function, which is just a straight line. Go ahead and actually do some application problems. Alright, first of all, let's look at linear versus exponential tables. We want to first determine, is it linear or is it exponential? And depending on which one it is, let's use the information that we get from the table to write an equation. Okay, cool. So let's look at our first table. So one nice thing about this is that all of our input values are going up by 1. Okay, so all we have to do is see what the output values are doing. And depending on what the output values are doing is going to tell us if it's exponential or linear. Now, what we can see is that when we start at an output of 100 and we go up by 1 unit in time, we're at 150. So we added 50. From 100 to 150, we added 50. From 150 to 200, we added another 50. From 200 to 250, we added another 50. Since we're adding by a constant number and not multiplying, this is linear. Okay, so this is going to be of the form y equals mx plus b. And instead of y, I'm going to be using h of t, and instead of x, I'm going to be using t, because those are my variables. Okay, so first of all, my slope is going to be this constant addend, or whatever we're subtracting by, or whatever we're adding by. So it's 50. So m is 50, and b is my y-intercept, or where my independent variable is 0, my starting value. So my starting value is 100. That's when t is 0. And now all we have to do is write our equation. So it's going to be y, which is h of t, equals m, which is 50, times x, which is t, plus b, which is 100. Okay, so that is our equation. Now let's take a look at the other table. So this time, again, this is nice because we're just going up by 1. And, if you're not going up by 1, you might not want to use this trick to compare to see whether it's linear or exponential, because you know, the idea that we're using is slope change per unit of time, per 1 unit of time. Okay, so it's important that these guys are 1 unit apart to use this trick, okay? And that is how they are here. They're all 1 apart. Okay, so let's take a look at the output values. So what's happening from 3 to 6? Well, we could say it's adding by 3, or we could say that it's multiplying by 2. From 6 to 12, we're adding 6, or multiplying by 2. From 12 to 24, we're adding 12, or multiplying by 2. So the adding, since these aren't all the same numbers, it's not linear, so get rid of that. It is exponential, though, because we have a constant multiplier, 2. So in our equation, y equals a times b to the x, remember b is going to be that constant multiplier, which is 2. So b is 2, that's our base, and a is our initial value, or our y-intercept, which in this case, when t is 0, f of t is 3. So that's our a. So to write this, since we're dealing with f of t and t, instead of y, I'm going to put f of t is equal to a, which is 3, times b to the t instead of x. So this is our exponential equation. And up here we had a linear equation. Alright, so are the values linear, exponential, or neither? So notice for both tables we're going up by 1 again for x's, so this is good. We can use our little trick here to see if it's exponential or linear. In the first table, I go from 32 to 26. Okay, so that's going to be 6 minus 6, right, to get from 32 to 26. From 26 to 20 is another minus 6. From 20 to 14 is minus 6. 14 to 8 is minus 6. So this is linear because we're decreasing by a set amount. We're subtracting. So adding and subtracting, linear. Multiplication, dividing, exponential. All right. So as time goes on, we're decreasing by 6 units per unit of time. So our slope is going to be -6, okay? Because we're decreasing. Now our y-intercept here is going to be the y value when x is 0. So that's going to be 32. And so our equation is going to be y, which in this case is g of x, equals m, which is -6, x plus b, which is 32. And that is our linear equation. Okay, what about the next one? So the next one, if I try to see what the difference between these numbers are, they're not going to be constant. So I can already do, if I do 17.68 minus 13.6, I get that this is a positive 4.08. And if I do 22.984 minus 17.68, I'm seeing that that's plus 5.304. So just from this, you can say, okay, it's not linear, because if it were, these numbers would have to be the same. So not linear. Let's check to see if it's exponential. So if it's exponential, we want to see if their ratios are the same. So for this one, I'll just see, okay, well, what's the ratio between 17.68 and 13.6? And that is, dun 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 dun, divided by 13.6, I'm getting 1.3. So from here to here, I have to multiply by 1.3. From here to here, again, I take the ratio. I say 22.984 divided by 17.68. Let's see what I get. I'm getting 1.3 again. So this is, again, times 1.3 to get to the next term. And you guys can check the other ones. This is times 1.3. This is times 1.3. So since we have a constant multiplier, this is going to be exponential. Alright, so exponential, we have y equals a times b to the x, where a is our starting value when x is 0. And that happens right here at 13.6. So a is going to be 13.6, and b is going to be my constant multiplier, and it's a positive 1.3. Okay, so what does that mean? What does the 1.3 mean? Remember last lecture we talked about that the b was either 1 plus or minus the percent change? Well, we know the percent change is 3, right? We know these values are increasing by 30% per unit of time. So anyway, our equation, instead of y, let's do f of x. So we have f of x is equal to a, 13.6, times b, 1.3, that's our constant multiplier, to the x. And that is our answer, you guys. That's exponential. Okay, is the function exponential? If so, find its initial value, its percent change, and its base. So we can do all of those things, no problem. Now let's take a look at our table. What's cool is these guys are all going up by 1, so we can use our multiplier trick to see if it's exponential. So I take the successive ratios between all of the terms. So the first ratio we would look at 7 over 28, and then we would look at, for this one, we would look at a 7 over 4, so the second one over the first one, and then for the other one, for the final one, we do 7 over 16 times 7 over 4. And if you calculate all of these, you can do it however you want in Desmos or whatever by hand. But the point is that you're going to get 1 over 4 for each of these. So each of these, to get from 28 to 7, you have to multiply by 1 over 4. To get from 7 to 7 over 4, you got to multiply by 1 over 4. And to get from 7 over 4 to 7 over 16, you got to multiply by 1 over 4. So that's our constant multiplier. Now, right off the bat, we can see this is exponential decay because 1 over 4 is smaller than 1. Okay, so that means that my b is my base. So my base is going to be the constant multiplier, which is 1 over 4. So yes, it's exponential because we have a constant multiplier. Alright, so my base is 1 over 4. It's exponential. The initial value is going to be the y-intercept, which is 28. So initial value is 28. And we found the base. Now the percent change, remember that our percent change was, we had a little formula for it. We had that the base was going to be equal to 1 plus or minus the percent change, and I'm trying to remember what I called it. I think I called it R, depending on if it was growth or decay. So plus was growth, and let's see if I can write this a little better. So plus was growth, and minus was decay, depending on what situation we had. Now we know this is decay because our base is smaller than 1. Remember, if b is between 0 and 1, it was decay. And if b was, maybe we should say the absolute value of b was greater than 1, we had growth. Here, 1 over 4 is between 0 and 1, so we have decay, so we use the minus. So b is equal to 1 minus r in this case, and so that tells me that since my b is 1 over 4, you can look at it like I mean, you can look at it a couple different ways. b is 1 over 4. That equals 1 minus some number r. You can solve this equation if you want. You can subtract 1 from both sides to give you 1/4 minus 1 equals negative r. 1/4 minus 1 is going to be negative 0.75. Divide both sides by a negative 1 to get our percent change is 0.75. So we're decreasing by 75% for each unit of time. So that was the percent change. Okay, so we covered that, yes, exponential, initial value. Now the next question says, if x is 8, what is f of x? Well, let's write our formula first. So formula is y equals a times b to the x, where a is our initial value and b is our base. Well, we found out what our base was. Our base was going to be 1/4. So we have y is equal to our initial value, which is 28, times 1 over 4 to the x. And we want to know what is f of 8. So if I plug in 8 into my function, what do I get for f of x? Maybe I should have called this f of x. So we get f of x is equal to 28 times 1/4 raised to the 8th. And if I put that in my calculator, okay, I'm getting a small number. So I'm getting about 4.27 times 10 to the negative 4. So that just means, move this decimal place to the left 4 units. And let's see. Yeah, so you get 0.000427. Alright, so a population has size 6,000 at time t equals 0 with t in years. If the population increases by 800 people per year, find a formula for the population at time t. Alright, so you want to ask yourself, is this linear or is this exponential? And how did we know? Well, it has to be linear because we're increasing by a constant amount. So let's write that down. Linear because we are increasing by a set amount per year. Okay, so that's how we know it's linear. So what's the equation going to be? Well, remember, linear is y equals mx plus b. In this case, we're calling y p because that's our population, and we're calling xt because that's our time. So population is our dependent variable, and it depends on time, which is our independent variable. So we have p is equal to mt plus b. So what's m? M is the amount that we're changing per unit of time. So it tells us here that we're increasing by 600 per year. So m is 600, and b is going to be the starting value, so our y-intercept. And that is going to be 6,000. They tell us that the population starts at 6,000 because that's when time equals 0. So our b is going to be, oh, and actually I meant this to be 800, sorry. Our b is going to be 6,000. And therefore, our equation is going to be p equals m times t plus b. And that is our answer right here. That is our equation. So we should be able to put in any value of t that we want and get a population out as our output. All right? Okay, So let's consider the same situation, but instead of increasing by a set amount, let's say that we're increasing by 8% every year. Okay, so that's not a set amount, right? 8%, if you're increasing by a percent every year, that's not the same amount every year, right? We saw that with the saving, whatever it was, 5% of $20 every day, or however much money you have, saving 5% of that every day. So the idea is that if it's increasing by a percent, increasing or decreasing by a percent, then that is exponential. So we know this is exponential, and we need to figure out what the growth rate is. It is increasing, so it's growing. So our base, if we have y equals a times b to the x, our base b, our growth rate, is going to be 1 plus 8%, which is 0.08. Again, it's 1 plus because we're growing. And so b is going to be equal to 1.08. And a is the same thing as in the previous problem. So a is still our y-intercept. So it starts at 6,000, so that's our a value. Okay, so we have everything we need. So now instead of y, again, I'm going to put p equals a, which is 6,000, times b, which is 1.08, to the t. So that is our model. This is our exponential model. And up here, we have our linear model. Alright, so there were 210 million licensed drivers in the US in 2010 and 222 million in 2016. So for part A of this question, we want to find a formula for the number n of licensed drivers in the US as a function of t. So that tells us that n is going to be our dependent variable acting like y, and t is going to be our independent variable acting like x. Okay, so as a function of t, the number of years since 2010, assuming the growth is linear. So they want us to write a linear function based on the information given. Now, a linear function needs two things. It needs a slope, and it needs a y-intercept. So how can we find these two things to write our function? Well, the y-intercept is b, and that's our starting value. So, the stuff that we're told is up here. And so the starting value is going to be in the year 2010, right? Because the function is going to, our input is going to be time since 2010. So we're treating 2010 as if it's like time 0, basically. So anyway, our starting value is 210 million. I'm just going to put 210, and we're going to just say that that's 210 million. And our slope is going to be the rate of change. So how much are we changing? Well, to find slope, remember we need 2 points. So for slope, we did dependent minus dependent over independent minus independent, y2 minus y1 over x2 minus x1. We're actually given 2 points here. And maybe pause the video and think what those 2 points are, what the x value is, what the y value is, and how we can compute the slope. Okay, so the first point is going to be, so our input variable is t, our output variable is n. So one point that we have, and t, by the way, is time since 2010. So when t equals 0, we're in 2010. And there are 210 million licensed drivers there. So one point that we have is 0, 210. Another point that we have is going to be is going to correspond to 222 million in the year 2016. Now remember, our t isn't going to be 2016. Our t is going to be the time passed between 2010 and 2016. So 2016, the difference between those 2 years is 6. So our time is 6. And that is going to correspond to 222 million licensed drivers. So this is another point. And now that we have this, we can go ahead and plug this into our formula. Remember, n is acting like our y's, and t is acting like our x's. So to find the slope, I can just do y minus y over x minus x. And let's see what I get when I do that. Alright, so I get 2. So our slope is 2. And that's all. That's it. That's all we needed. So our equation is y, which is n, equals m, which is 2, times x, which is t, plus b, which is 210. So this models the number of licensed drivers in the year after, however many years have elapsed since 2010, t. And that's if this were linear. Now let's take a look at part B. So it says, now let's assume that the situation is exponential. Alright, so now we want to find a formula, again, for n, of the number of drivers since 2010, assuming it's exponential growth. So we need 2 things for exponential growth. We need the initial value, which we know, it's 210 from the linear part. We already said, okay, that's the starting value is 210. And we also need the base. We need the growth or decay rate. Now we're growing here, so we know it's going to be a growth rate, but we're not really sure how to get there. We do have the 2 points that we can utilize, and the 2 points are 0 to 10. This was Tn, and then we had that other point 6, comma 222. Right, and the goal is to find b. So I know that the formula is going to be of the form y equals a times b to the t. And what I can do at this point is notice that I have a, I have a t, and I have an n. So I can just use that to solve for b. So you're not going to want to use this one because it's not going to give you any new information, but we can use this one right here. We can sub in 222 for n. We can sub in 6 for t, and we know what a is. A is 210. So we have 222 for n equals 210 for a times b, which we are trying to find, all raised to the 6th. And now we have everything in one variable. We can solve for b. So the first thing you can do is you can undo multiplication by 210 by dividing both sides by 210. Sorry, that's the cat. And doing that, well, let's just leave it like that for now. So we have 222 divided by 210 is equal to b to the 6th. And how can we undo a power of 6? Well, we can 6th root both sides, right? Just like when we undo a square, we square root both sides, but 6 rooting is kind of weird. Your calculator probably doesn't have it. So 6 rooting corresponds to, let's say we have the 6th root of b. That corresponds to b to the 1/6. Just like if we have the square root of b, that corresponds to b to the 1/2. So the idea here is to undo this, we need to raise it to the 1/6, because when we do that, when we raise both sides to the 1/6, this is going to go to 1. And so we have b is equal to 222 over 210 to the 1 over 6, and we can see what that is in the calculator. So that is about approximately 1.0093. So that is our b value. We know what our a value is. So our exponential function, plugging in a and b, is going to be n equals 210 times b to the t. And that is our exponential model. Okay, so let's do this example. So we have g of x is an exponential function. It's in exponential function form. It says if g of 0 equals 60 and g of 3 equals 14, find g of x. Okay, so what we're really trying to do is we're trying to figure out what a is and we're trying to figure out what b is. Once we have those two things, we have our answer. So a is going to be our initial value. This is our y-intercept. And a y-intercept always occurs when x is 0. So look at the information we have. We have g of 0 equals 60 and g of 3 equals 14. So this first piece of information is telling us what our a value is. It says when our x value, when our input is 0, our output is 60. So when x is 0, y is 60. So that's our a value, is 60. So our a value is 60, and we have that piece, and now all we need to figure out is our b value. And we can use this other piece of information to get that. So using this format right here, we have g of x is equal to a, which we just said was 60, times b to the x. And the x and the g of x correspond to a point, right? G of x is like your y, and x, of course, is your x. So we're told this additional point here that when x is 3, y, or g of x, is 14. So we can plug this information in, and we can say, okay, well, we have 14 is equal to 60 times b to the 3, just plugging in g of x and x, and now we can solve for b. So if I draw my line through here, I want to isolate b, so I can first divide 60 on both sides to get rid of that. And so I get 14 over 60 is equal to b to the 3. And just like when we looked at the 6th root of something equaling b to the 1/6, the third root, if we want to third root something on both sides, that's the same thing as taking the 1/3 of both sides. Okay? So what I'm going to do to get rid of that 3 is I'm going to raise both sides to the 1/3. And that way this clears out to 1, which is what we wanted. And we get b to the 1st equals 14 over 60 to the 1/3. And let's go ahead and do some rounding there. So we have 14 divided by 60, raised to the 1 divided by 3. And I'm getting about 0.6156 for my b value. We have a, we have b. Now all that's left to do is write our equation. So we have g of x is equal to a times b to the x. And this is our answer. This is the equation that we wanted. And notice that right here tells us this is exponential decay. We're actually decreasing the amount of whatever we're talking about as time gets bigger. And we know that because this is between 0 and 1. Okay, let's do another example. So we're given 2 points this time. Unfortunately, one of those points is not the y-intercept. So we need to set up 2 equations to figure out what our a and our b values are. So first thing is we're going to have this general form g of x equals a times b to the x. Alright, and we know in x comma g of x, we don't know an A and we don't know a B, right? Because we don't know A because we have 2 and negative 1, G of 2 and G of negative 1, and neither of our inputs are 0, so we can't determine what A is. However, we have an x comma g of x. We have a 2 comma 5 over 64, so this is x comma g of x. And we have another one, we have negative 1 comma 40. Okay, so this is all the information we have. Now let's go ahead and set up 2 equations. The first equation, we can say, okay, well, g of x, I'm using the first point. I'm saying g of x is 5 over 64, and that's going to equal a, which we don't know, times b, which we don't know, raised to the second power. So I was just plugging in x and g of x into the equation. Now, if we plug in the other point into our other equation, we get g of x, which is 40, equals a times b to the negative 1. Okay? So, this is all I have to work with right here. And when you have, so, when you talked about this in intermediate algebra, we talked about systems of equations in intermediate algebra. So basically, we can isolate a variable and punch it into the other equation to solve for the variable. So right here, what I notice I can do is I can get a by itself, because the idea is that you want only one variable in an equation. So in the second equation, to get a by itself, well, first of all, I actually can rewrite this to be a little bit nicer. Instead of a times b to the negative 1, I can write this as a times 1 over b, right? It's the same thing. So, so this is just 40 equals a over b. And if I multiply both sides by b to isolate a, I get that a is equal to 40 times b. So that information I got from equation 2. I just rearranged it so that a was on one side by itself. Since a is 40 times b, I can plug that in up here and b just in terms of b. So let's go ahead and do that. So up here we have 5 over 64. Instead of a, I'm replacing with what I just found. A is 40 times b. So I have 40 times b squared. And so 40b times b squared, well, b times b squared is b cubed. So this becomes 40b cubed is equal to 5 over 64. Okay, now I can isolate b. So I can isolate b by, let me erase some of this so I have some more room. I can isolate b by dividing both sides by 40 or multiplying by 1 over 40. It's the same thing. And so I get b to the third is equal to, let's go ahead and just multiply this out and simplify it. Let's see. Let's see what we get. Okay, so I'm getting 1 over 512. And so to get b by itself, I want to undo a cube. So I want to take the third power of both sides to undo that cube. So that clears. And I'm left with b is equal to 1 over 512 to the 1/3. Okay, so that's going to give me 1 over 8. Okay, so b is equal to 1 over 8. And so a by our equation that we found over there. So let me write it over here. B is 1 over 8. Since B is 1 over 8, that means that A is 40 times 1 over 8, which is 40 times 1 over 8 is 40 divided by 8, which is 5. Alright, so we found A and B. So our answer here is g of x is equal to 5 times b to the x. And that is our final answer. Okay, so find a formula for the exponential functions. So again, we just need two things. We need a and we need b. And then we have an exponential function. Because our exponential function can be written as y equals a times b to the x, or whatever your dependent, independent variables are in this case. In this case, it looks like our dependent, acting like our y, is f of x. So let's go ahead and sub that in with f of x. Our independent is x. Okay, so we want it to be of this form, and all we need are a and b. Now a is our initial value, or our y-intercept. So that occurs when x is 0, right? And so when x is 0, we can see that our output is 3. So a is going to be 3. And b, we're not sure, but what we can look at is we can do this a couple different ways, but one way is to just look at the constant multiplier, right? If we look at between what happens for 1 unit of time, so between 1 and 2, for example, we can see that this guy has 6 as an output, and this guy has 12. So if you were to make a little t-chart, we would have 1, 6, and then 2, 12, and we know that this is exponential, so this is going to be times 2, and so the next one at 3 should be at 24, and the next one should be at 48, and so forth. So this guy is going to be our b value. This is going to be 2. Now, you could have figured this out in another way, but, that's the easiest way to do it, I think. So, our answer is going to be f of x equals a times b to the x. So that is our function that represents this exponential curve. Okay, so we want to find a formula for this exponential function, but notice that we're not given our initial value a. It looks like it could be about 2.5, but we're not sure from the picture. So we want to go ahead and use the points that were given instead to figure out our function. So our exponential function is going to have the form f of x equals a times b to the x, and our job is to figure out what is a and what is b. Okay, so what's given are these 2 points. So the first point, we can say this is an x, it's -2, and then our output is going to be f of x in this case, so that's going to be 6. And then we have another one down here, 2 is x, and 1 is f of x. So we can write 2 equations for this to figure out a and b. So our first equation with our leftmost point, we can say, okay, using this up here, we have f of x, which is 6, equals a, which we don't know, times b, which we don't know, raised to the -2. And then our second equation we can write from this point. So we have f of x, which is 1, equals a times b to the 2. Okay? So if I use equation 2 to isolate a, I can do that by dividing both sides by b squared. And I get that a is equal to 1 over b squared. Now, because I know what a is in terms of b, I can plug that in here so that I can get everything up here in terms of b. That way I can get a number for b. So, using that information, I get 6 is equal to 1 over b squared. Again, I'm just plugging in 1 over b squared, subbing it in for a, times b to the -2. Now b to the negative 2 is 1 over b to the 2. So this becomes 1 over b2 times 1 over b2, and that equals 6. Multiplying straight across, I get 1 over b to the 4th equals 6. Okay? Now what I can do to get the b to the 4th out of the denominator is I can multiply both sides by b to the 4th so that it's out of the denominator. And I can divide both sides by 6 to give me b to the 4th equals 1 over 6. And finally, to get b alone, I can take the 4th root of both sides. So b is going to equal 1 over 6 to the 1 over 4. Okay, and that's a number. Whatever number that is, I'm not sure, but it's a number. We can use b right here to get a, to get a number for a. So we know that a is equal to 1 over b, which we just found was 1 over 6 to the 1 over 4, and that's all going to be squared. So if you put this in your calculator or on Desmos, just simplify it out, you can do that, and let's see what we get. So we get 1 over 6 to the 1 over 4 to the second, and then 1 over that. So I'm getting that a is approximately 2.4. And then b, when we crunch this in Desmos, or your calculator, when we do 1 over 6 raised to the 1 over 4, we're getting about 0.64. And that makes sense with our picture because this is our a, and it looks like it's almost 2.5. It's not quite, though. Good thing we didn't guess that. It's 2.4. Pretty close, though. And then b is less than 1, which tells us it's exponential decay, which we can see, right? As our time goes on, we're getting smaller and smaller and smaller. That's exponential decay. So this does make sense. And so our function is going to be f of x equals a times b to the x. And that is our answer there. All right, let's do one more. So it says find a formula for the function shown. So even though we haven't talked about exponential graphs, just know that, you know, for the sake of this section, our exponential graphs are going to look like this if it's exponential growth. And again, we're going to go more, you know, in depth with this next time, but this is exponential growth, so as time goes on, we're getting higher and higher, and then exponential decay is going to kind of look like this. So this is exponential decay. As time goes on, we get smaller and smaller, closer to the x-axis, or yeah, usually. So that's exponential, and we also have a line right here. Now let's go ahead and find the equation of the line first. Now we only need 2 points for a line. And really we need two things for a line. We need the slope and the y-intercept. Now it's pretty clear that the y-intercept here is 1, right? Because it's right in the middle of 0 and 2, so that has to be 1. So our b is going to be 1 for the line. And then we can do we can find our slope. We can do it a few different ways. I mean, we can do rise over run, or we can find another point and subtract the ordered pairs and divide and all that stuff. But I'm going to just do rise over run. So if I start at 1 and I rise up to get to this next point, the black point, I'm going to rise up, let's see. So I go 1 and then 2, 3. So I rose up 3 because I went from 1 to 4, so I went up 3. And then I run, well, let's see, I'm going from x equals 0 to x equals 1, right? That's 1. So my slope is going to be positive 3 over positive 1, which is 3. So my line equation is y equals 3x plus 1. Okay. So let's figure out what the exponential equation is going to look like. So the b is going to be the b of the exponential because they both meet right there. So that's, they share a y-intercept basically. So that guy is our a value, and that's 1. So it's the same as our b in the line. Now our actual base in the exponential function we need to figure out. And we can figure that out by just finding a point on the exponential curve and plugging it into our basic equation. So let's see, this guy looks like a good point. So this point on the exponential curve is 1, 3. So x is 1, y is 3. And I can use that in my basic formula, y equals a times b to the x. I can just plug in y, a, and x and get out a b. So my y is 3, my a is 1, we're not sure what b is yet, but x is 1. So this is kind of nice on the right side. That's just 1 times b, which is b. So b equals 3. So that is our answer there. And now that we have that, our formula is going to be y equals a, which you don't have to write the 1, but I'll just do it for the sake of learning this stuff. You guys learning this stuff. So this is 3 to the x, and this is our exponential equation down here. And this was our line. This was our linear equation up here.